Section 5.3, Antiderivatives and Indefinite Integrals. A function f of x is an antiderivative of a function f of x if capital F prime of x is equal to f of x for all x in the domain of f. The process for finding an antiderivative is called antidifferentiation. The family of all antiderivatives of the function is the indefinite integral of f with respect to x. So we talked about this a little bit in class today, but the antiderivative is basically the opposite of the derivative. So notation for antiderivatives, also called indefinite integrals. If dy dx equals f of x, then y is equal to the integral sign of the integrand. So the integrand would be whatever the derivative function is, dx, which tells me what I'm integrating in terms of. So I'm going to integrate so that it's in terms of x. We call it the variable of integration, is equal to capital F of x. So this is now the original function before it gets differentiated. Right, so this is the antiderivative of this function plus the constant. Okay, so we talked about this in class today. The constant is very important because we can find the derivative of a lot of functions that will give us the same derivative, but the constant is the thing that's different. Right, so the derivative of x squared is 2x, but the derivative of x squared plus 3 is also 2x. Right, so because of that, we need to make sure that when we are anti-differentiating, we want to make sure that we take into account the constant. So we add the c at the end. So let's look at a few examples. So the left column is all of my derivatives. The right column, I'm trying to find the antiderivative, so the original function. So if I have a derivative of 3x squared, my antiderivative is x cubed plus c. Right? So the way that we write that we're finding antiderivative is the integral sign of the derivative in terms of x, so dx. And the answer would be x cubed, because if we take the derivative of x cubed, we get 3x squared plus our constant c. Okay, so if we were to take the derivative of x cubed, we know we would have to bring down the 3 and then subtract 1 from the exponent. So here we know we have to, if we're working backwards, we're going to add 1 to the exponent, which will give us 3, and we're going to divide this number by our new exponent. So 3 divided by 3 is 1, sorry. So we'll get 1x cubed plus c. Okay, and then here now we have a derivative of -4. So we're going to rewrite this so that we can find the integral of -4 in terms of x. And that's going to give us -4x plus c. The derivative of -4x is -4. The next one, we have the integral of 6x dx. So we know our exponent, we're going to add 1 to that, so we should have x squared. And then if we divide 6 by 2, we get 3, so we have 3x squared plus c.
Good afternoon. Stephen Ellis, please come to the main office. Stephen Ellis to the main office.
Announcements. And now we have a derivative of x to the 4th. So to find the integral of x to the 4th dx, we want to add 1 to the exponent, so we have x to the 5th. And then we're going to divide the coefficient by our new exponent, so 1 divided by 5 plus c. Right, and here, this last one, we have the integral x to the -3 dx. So we're going to add 1 to the exponent, and that'll give us x to the -2. And then we'll divide our coefficient by our new exponent. So 1 divided by negative 2 is negative 1/2 plus c. Which we can rewrite as negative 1 2 x squared plus c. Because x to the negative 2 is just x squared at the bottom of my fraction. Okay, so we have a few more examples on the next page. These examples on the next page look a little bit different, and we have to rearrange some things or rewrite some things to find those antiderivatives that we're looking for. So, this first one, the derivative is the square root of x, which we're going to rewrite as x to the 1/2. So then we are looking for the integral of x to the 1/2 dx. So now, again, we're going to add 1 to the exponent, so we have x to the 3/2. And then we're going to divide our coefficient by our new exponent. So 1 divided by 3 over 2 is 2 over 3 plus c. And we can rewrite that, if we wanted to, as 2 over 3 square root of x cubed plus c. Our next derivative, we have x to the negative 1, which we can rewrite as 1 over x. So we're looking for the integral of 1 over x dx. And now if we were to think back to what equation gives me a derivative of 1 over x, we know that's ln x, right? The derivative of ln x is 1 over x. So we have ln x plus c. Now f prime is sine of x, and so we're looking for the integral of sine of x dx. Now what gives me a derivative of sine? Cosine comes the closest, right? The derivative of cosine is negative sine, but we want a positive sign, so we're going to make this negative. The next one we have secant squared x, so we want the integral of secant squared x dx. And what gives us a derivative of secant squared x? Tangent. So tan of x plus c. Always remember your plus c. Now this last one's a little bit tricky. Right, we want the integral of e to the 3x dx. Now, what function gives me a derivative of e to the 3x? Right, the derivative of e to anything is e to itself, right? So we know that we're going to have e to the 3x plus c, right? The derivative of e to whatever is going to be itself. But now, here, we know we would have to do baby mama, right? E to the 3x, but we also want to take the derivative of 3x. So the derivative of 3x we know is 3. But if we look at our integrand, there's no 3 up front. So we need to find a way to get rid of that 3. So if we take 3 and multiply it by 1/3, we just get 1, right? And we don't usually write a coefficient of 1. So we know that to take the derivative of 3x and have it equal 1, we need to have a 1/3 up front. So now when we take the derivative of e to the 3x, we get e to the 3x. And when we take the derivative of 3x, we get 3. And when we multiply that by 1/3, we get 1, which is the coefficient that we wanted. So this is the anti-differentiation of our original derivative. Okay. So in class I talked a little bit about how in the notes tonight, you're going to figure out how to find C. So this next section, using initial conditions, is going to help you to identify what C is. So to find C, we need to be given a derivative and an initial condition, or a condition of some sort, which will usually come in the form of a point. So for this example, we want to find the function with the given derivative whose graph passes through the point P. So this is asking us to find the antidifferentiation of this derivative at the point 4, 3. So this means f of x is going to equal the integral of f prime of x dx. And f prime of x we know is 3 root x minus 5, which we're now going to rewrite as 3 x to the 1/2 minus 5 dx. So now, to find the integral for this, right, we're going to add 1 to this exponent. So we're going to have f of x equals, we're going to add 1 to the exponent, so we'll have x to the 3/2. And then we're going to divide this number by our new exponent. So 3 divided by 3 over 2 is 2. And then the derivative, the antiderivative of negative 5 is negative 5x. And then we're going to add our plus c. So this is what we call the general solution. When our solution still has a c, it's the general solution. It's the general integral, indefinite integral. So now we know that we have this point 4, 3. So we're going to plug in the point 4, 3 into this equation so that we can solve for c. So f of 4 is going to equal to 4 to the 3/2 minus 5 times 4 plus c. So f of 4 we know is 3. So 3 times all equals 2 times 8 minus 20 plus c, which is equal to 16 minus 20 plus c. So c is equal to 7. So we have f of x is equal to 2x to the 3/2 minus 5x plus 7. And this is what we call a particular solution. Okay, now for example number 2, we want to find the function f of x if f double prime of x is equal to 12x plus 4, f prime of 1 is equal to 3, and f of 1 is equal to 5. So this is actually going to require us to anti-differentiate 2 times because we're starting with f double prime and we want to get to f. Okay, so first thing we want to find is what is f prime of x, right? So f prime of x would be undoing f double prime, right? So we want to take the integral of f double prime of x dx. So f prime of x is equal to the integral of 12x plus 4 dx. So f prime of x is equal to Now we're going to add 1 to our exponent, so we have x squared, and we're going to divide this number by our new exponent, so we have 6. So 6x squared plus 4x plus c. So that's our general solution for our first derivative. Now this problem tells us that f prime of 1 is equal to 3. So this problem requires us to find the particular solution, right? We can rewrite this as a point, so 1, 3 is our point here. So we're going to find the particular solution for the first derivative at the point 1, 3. So we are going to plug in f prime of 1 is equal to 6 times 1 squared plus 4 times 1 plus c. So 3 is equal to 6 plus 4 plus c. So this c is equal to -7. So our particular solution for f prime of x is equal to 6x squared plus 4x minus 7. So that's our particular solution for f prime of x. Now this problem is specifically asking for f of x. So now we have to integrate this one more time using f prime of x. So we know that f of x is equal to the integral of f prime of x dx. So f of x is equal to the integral of 6x squared plus 4x minus 7. So f of x is equal to, add 1 to the exponents, we have x cubed, 6 divided by 3 is 2, plus add 1 to the exponent, so x squared, 4 divided by 2 is 2, and then -7x plus c. So we could be done here, but this problem gives us the initial condition, or a condition, for our f of x function. So this, written as a point, is 1, 5. So this problem is asking us for the particular solution of f of x at the point 1, 5. So we'll plug in what we know. And we'll solve for c. So we have 5 equals 2 plus 2 minus 7 plus c. So c is equal to 8. So our particular solution is f of x is equal to 2x cubed plus 2x squared minus 7x plus 8. And if you differentiate this twice, right, if you find the second derivative of this, you should get all the way back to 12x plus 4. And that's how you would check your answer. Now this last problem is very similar, except now it is bringing you into a real-world situation. So a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. We want to find the position function, s of t, given the height s as a function of time t. And it gives us the function a of t, which we know is acceleration, is equal to -32 feet per second squared. So to get from a of t to s of t, so this is acceleration, we need to first find the velocity function, and then we can find the position function. So to find the velocity function, we need to integrate, or find the integral of a of t dt. Right, so this now becomes dt because our function is in terms of t, not in terms of x. So what we're going to do is we're going to plug in what we know. So the integral of a of t we know is negative 32 dt. So if we were to anti-differentiate that, we know v of t is going to equal negative 32 t plus c. Okay. So this is, again, the general solution. But to keep going, we're going to need the particular solution to integrate. So going back to what we know, this is saying that we have an initial velocity of 64 feet per second. So if it's the initial velocity, that means that when time is 0, so at t equals 0, v is equal to 64. So if we were to plug all of that in, we know v of 0, negative 32 times 0, let's see. So v of 0 we know is 64. So c must equal 64, right? Because negative 32 times 0 is 0. So c equals 64. So v of t is equal to negative 32 t plus 64. So now we're going to use that information to integrate to find the position. So we know position, s of t, is going to be equal to the integral of v of t dt. So s of t is equal to the integral of negative 32t plus 64 dt. I put parentheses around these when we have multiple terms to emphasize that we're taking the integral of the whole thing, not just the first piece. Okay. So s of t then must equal, right, we're going to add 1 to the exponent, so we have t squared. And we're going to divide our coefficient by our new exponent, so negative 16 t squared. And then plus 64 turns into plus 64 t, and then we have the plus c. Okay, so this problem says that we have an initial height of 80 feet. Now, if that's our initial height, that means that at t equals 0, s, which we are saying is the variable for height, is equal to 80. So s of 0 is equal to negative 16 t squared plus 64, oops, these are zeros, times 0 plus c. So 80 is equal to negative 16 times 0 squared plus 64 times 0 plus c. Both of these turns into zeros, so 80 is equal to c. So the position function, s of t, is equal to negative 16 t squared plus 64 t plus 80.